Welcome! In this video, we'll be exploring LeetCode problem number 1619, titled Mean of Array after removing some elements. This problem challenges us to calculate the mean of an array after removing the smallest and largest 5% of its elements. We'll dive into the solution step by step, considering different approaches and their complexities. Let's get started. In this problem, you're given an integer array ARR and tasked with calculating the mean of the array after removing a specific portion of elements. Specifically, you need to remove the smallest 5% and the largest 5% of the elements in the array. Once those elements are removed, the mean is determined as the sum of the remaining numbers divided by the count of those numbers. The result should be calculated with a precision of up to 5 decimal places. The input array can have between 1 and 10,000 integers, and each integer falls within the range of -100,000 to 100,000. The output, in turn, will be a floating point number representing the mean after the specified removals. Let's look at an example to clarify. Suppose the input array is 1, 2, 2, 2, 3, 4. The array contains 6 elements, and 5% of 6 is 0.3. When this value is rounded down, we get 0, meaning no elements are removed from either side of the array. The array remains unchanged, and the mean is calculated as the sum of all its elements divided by the total number of elements. Here, the sum is 14, and dividing by 6 gives us a mean of 2.66667. This highlights how the problem handles cases where rounding results in no elements being removed. Next, here's another example with the array 6, 2, 7, 5, 1, 2, 0, 8, 5, 10. This time, the array has 10 elements. Calculating 5% of 10 gives 0.5, and again rounding down results in 0. Therefore, no elements are removed from either side of the array. After sorting the array, we have 0, 1, 2, 2, 5, 5, 6, 7, 8, 10. The mean is then calculated as the sum of all these numbers divided by 10. The total sum is 46, so dividing by 10 results in a mean of 4.00000. This demonstrates that even with a larger array, no removal occurs if the 5% calculation rounds down to 0. Finally, consider the example where the array is 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. Here, the array contains 10 identical elements. Removing the smallest 5% and largest 5% still results in 0 elements being removed, as before. The array remains 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, and the mean is simply calculated as the sum of all elements divided by 10. The total is 40, and dividing by 10 gives a mean of 4.00000. The problem also provides some constraints and edge cases to consider. For example, arrays with the minimum length of 20 will have exactly one element removed from each side. Arrays with all identical values or containing negative numbers are other scenarios to keep in mind. These considerations ensure the solution is robust and handles all possible cases effectively. To solve the problem of finding the mean of an array after removing the smallest and largest 5% of elements, we can start by considering a straightforward approach. A brute force method involves sorting the array and then filtering out the smallest and largest 5% of elements. Sorting places the elements in ascending order, making it easy to identify the values to remove. The process involves calculating the number of elements to exclude, which is determined as 5% of the array's length, rounded down. Once the array is sorted, we can slice off the first and last segments of size k, leaving only the middle portion. The mean is then calculated by summing the remaining elements and dividing by their count. While this approach is simple and intuitive, its time complexity is dominated by the sorting operation, which is O, n log n. This makes it efficient for moderate-sized arrays but potentially slow for very large datasets. While the brute force approach is easy to implement, it comes with trade-offs. On the positive side, it is straightforward, requiring only sorting and basic arithmetic operations. However, the reliance on sorting makes it less optimal for extremely large arrays, where the O, n log n, complexity can become a bottleneck. To address this, we can consider an optimized approach that avoids sorting the entire array. Using a selection algorithm like quick select, we can directly find the thresholds for the smallest and largest 5% of elements. Quick select allows us to determine the kth smallest and nkth largest values more efficiently. Once we have these thresholds, we can iterate through the array, summing up only the elements that fall between them. This avoids the overhead of fully sorting the array, achieving an average time complexity of O(n). However, it's important to note that while this method is faster, it introduces additional implementation complexity due to the quick select algorithm. For datasets with specific characteristics, such as integers with a small range of values, we can explore an alternative approach based on frequency counting. This method involves using a frequency array or hash map to count occurrences of each unique value in the dataset. By traversing the frequency array, we can determine the cumulative counts and identify the smallest and largest 5% of elements without explicitly sorting. Once these elements are excluded, the mean of the remaining values can be calculated. The efficiency of this method lies in its linear time complexity for counting and summing, which makes it particularly effective for small-range integers. However, for datasets with large value ranges or floating-point numbers, this approach becomes impractical as it would require excessive memory or additional precision handling. Therefore, while this method is highly efficient in specific scenarios, it is not universally applicable. After evaluating the different approaches, the sorting and filtering method emerges as the most practical and balanced solution for this problem. Although optimized alternatives like quick select or bucket counting can reduce time complexity in specific situations, their added implementation complexity is unnecessary given the problem constraints. Sorting provides a clear and reliable way to handle edge cases, such as duplicate values or floating point numbers, while maintaining correctness. Additionally, the problem guarantees that the array size is large enough to remove 5% from both ends, simplifying edge case handling. Sorting not only ensures a deterministic process for identifying the values to exclude but also makes the computation of the mean straightforward. With a time complexity of O(n log n, this approach strikes a good balance between efficiency and simplicity. It is easy to implement, debug, and maintain, making it the best fit for solving this problem in a general context. To solve this problem, we need to calculate the mean of an array after removing the smallest 5% and largest 5% of its elements. This involves three main steps: sorting the array, removing a certain percentage of elements from both ends, and then calculating the mean of what remains. The constraints of the problem ensure that the input array is always non-empty and contains at least 20 elements. This is important because it guarantees that removing 5% from both ends will still leave enough elements to compute a meaningful mean. Now, let's break this down step by step. First, the input is an array of integers, and the output is a floating point number representing the truncated mean. A key constraint is that the size of the array, denoted as n, is always at least 20. The truncation size, calculated as k equals floor, 0.05 *n, determines how many elements to remove from both ends. For example, if the array has 20 elements, 5% of 20 is 1, so k equals 1. This means we will exclude one smallest and one largest element before computing the mean of the remaining values. Once we've determined the truncation size, the next step is to sort the array in ascending order. Sorting is essential because it organizes the smallest elements at the beginning and the largest elements at the end, making it easy to remove them. After sorting, we can exclude the first k elements and the last k elements using slicing. For example, if the sorted array is 1, 2, 3, 4, 5, and k is 1, the remaining array after slicing will be 2, 3, 4. This trimmed array contains only the elements we want to include in our mean calculation. Finally, to compute the mean, we sum up the values in the trimmed array and divide by the number of elements left. This ensures the result is a floating point number, which is typically required for problems involving averages. The last step is to return the calculated mean, formatted as specified in the problem statement. There are several key insights to note about this algorithm. First, sorting is an essential step because it simplifies the truncation process by allowing direct slicing of the smallest and largest elements. Second, the truncation size, k, is always 5% of the array size, making the algorithm predictable and easy to implement. Third, in terms of performance, the sorting step has a complexity of O(n log n, and the slicing and mean calculation are O(n), so the overall efficiency is dominated by the sorting step. Now, regarding data structures, the input array itself is sufficient for this algorithm. Arrays are ideal here because they allow efficient indexing and slicing operations. Importantly, no additional data structures are needed, keeping the implementation straightforward. Finally, let's consider some edge cases. For the smallest allowed array size of 20, only one element is removed from each end. For very large arrays, the algorithm remains efficient due to its O, n log n, complexity. And if all elements in the array are identical, the mean will remain unchanged after truncation, since slicing identical values doesn't affect the result. To wrap up, let's analyze the algorithm's complexity. The time complexity is dominated by the sorting step, which is O, n log n. Slicing the array and calculating the mean together take O, n, so the overall time complexity remains O, n log n. As for space complexity, the sorting can be done in place, meaning no extra space is required beyond the input array itself. This makes the space complexity O, 1, excluding the storage for the input. Together, these complexities ensure that the algorithm is efficient and scalable, even for large input arrays. With that, we've completed our deep dive into the algorithm. By combining sorting, slicing, and basic arithmetic, we can effectively solve the problem while adhering to its constraints and ensuring optimal performance. This Python solution solves LeetCode problem number 1619, mean of array after removing some elements. The problem asks us to calculate the mean of an array after removing the smallest 5% and largest 5% of elements. To achieve this, the solution follows these steps. 1. Sorting the array. The input array is sorted in ascending order using the sort method. Sorting ensures that the smallest and largest elements are grouped at the beginning and end of the array, respectively, making it easy to exclude them. 2. Calculating exclusion count. The number of elements to exclude from each end of the array is determined as 5% of the total array length. This is calculated as n//20, where n is the length of the array. Integer division is used to ensure the count is a whole number. 3. Trimming the array. Using slicing, the smallest 5% and largest 5% of elements are removed. The slice ARR, exclude_count, and exclude_count, selects the middle portion of the array, excluding the calculated number of elements from both ends. 4. Computing the mean. The mean of the remaining, trimmed, elements is calculated by dividing the sum of the trimmed array by its length. The result is stored in trimmed_mean. 5. Returning the result. Finally, the trimmed mean is returned as the output. This solution is efficient with a time complexity of O, n log n, due to sorting and is straightforward to implement. It handles all edge cases as the problem guarantees that the array contains at least 20 elements, ensuring the 5% calculation is always valid. The code is concise and easy to understand, making it suitable for production use. This is the Java implementation of LeetCode problem number 1619, mean of array after removing some elements. The logic mirrors the provided Python solution, with key differences being Java's use of type declarations, the arrays.sort method for sorting, and explicit loops to calculate the sum of the trimmed array. The method computes the mean after excluding the smallest and largest 5% of elements, ensuring efficient and precise calculations. To solve this problem, we start with the input array 6, 2, 7, 5, 1, 2, 0, 8, 10, 6. The first step is to sort the array in ascending order. Sorting the elements gives us 0, 1, 2, 2, 5, 6, 6, 7, 8, 10. Next, we calculate how many elements to exclude from both ends of the array. The total number of elements, n, is 10. To determine the number to exclude, we calculate n//20, which results in 0.5, and because this is integer division, it rounds down to 0. This means no elements will be removed from either the smallest or largest ends of the array. With no exclusions, the trimmed array remains 0, 1, 2, 2, 5, 6, 6, 7, 8, 10. Finally, we compute the mean of the remaining elements. Adding up the values in the trimmed array gives a total sum of 47, and since there are 10 elements, the mean is 47/10, which equals 4.7. The final output for this example is 4.7. Now, let's look at another input array, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. The first step is to sort the array, but since all elements are already the same, the sorted array remains 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. With 10 total elements, we calculate the number of elements to exclude using n//20, which again results in 0. Therefore, no elements are trimmed from either end, and the trimmed array remains 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. Next, to compute the mean of the trimmed array, we sum up all the elements. Each element is 4, and there are 10 elements, so the total sum is 4 plus 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 4, which equals 40. Dividing this sum by the array length, 10, gives us a mean of 40/10, which equals 4.0. The final output for this example is 4.0. Now, let's consider a larger input array, 9, 7, 3, 1, 5, 11, 15, 13, 17, 19, 21, 23, 25, 27, 29, 31, 33, 35, 37, 39. In the first step, we sort this array in ascending order. The sorted array is 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, 31, 33, 35, 37, 39. With 20 total elements, we calculate the number to exclude using n//20, which gives 1. This means we will exclude one smallest and one largest element from the array. After removing the smallest and largest elements, which are 1 and 39, the trimmed array becomes 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, 31, 33, 35, 37. To calculate the mean, we sum up all the elements in the trimmed array. The total sum is 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus 19 plus 21 plus 23 plus 25 plus 27 plus 29 plus 31 plus 33 plus 35 plus 37, which equals 350. The length of the trimmed array is 18, so the mean is 350/18, which is approximately 19.44. Therefore, the final output for this example is 19.44. To analyze the time complexity of this solution, let's break it down into its key operations. First, we sort the input array using Python's built-in timsort algorithm, which has a time complexity of n*log n, where n is the size of the array. Sorting is the most computationally expensive step. Next, we calculate the number of elements to exclude from both ends of the array, which is simply an arithmetic operation and takes constant time, 1. After that, we slice the array to remove the smallest and largest 5% of elements. Slicing in Python takes k time, where k is the size of the resulting array. Since we're keeping 90% of the elements, the slicing operation takes 0.9 n, which simplifies to n. Finally, we compute the mean of the trimmed array. The summation step iterates through the trimmed array, which also has n complexity, while dividing by the length of the array is an 1 operation. These steps give us a detailed breakdown of the time complexity for each part of the solution. By combining the time complexities of all the steps, we can summarize the total time complexity of this solution. Sorting the array dominates with n*log n, while slicing and summation each contribute n. Constant time operations like arithmetic calculations and the final division step add only 1. Since the sorting step has the highest growth rate, it determines the overall time complexity of the solution. Thus, the total time complexity is n*log n, making sorting the bottleneck of this approach. Now let's evaluate the space complexity of this solution. First, we consider the input array. The array itself occupies n space, as it contains n elements. Next, Python's timsort algorithm sorts the array in place, so no additional storage is required for sorting beyond a small constant amount of auxiliary space, which is 1. However, when we slice the array to create the trimmed version containing 90% of the elements, a new array is created. This slicing operation uses 0.9 n space, which simplifies to n. Finally, the scalar variables used in the computation, such as exclude_count, n, and trimmed_mean, take constant space, 1. This gives us a clear picture of the space usage for each part of the solution. Adding up all the space contributions, we find that the input array requires O(n) space, and the slicing operation also adds O(n). The auxiliary space used during sorting is negligible at O(1), and other variables are constant in size. Therefore, the total space complexity is dominated by the input array and the resulting slice, which both scale linearly with the size of the input. This leads to an overall space complexity of O(n). To compare this solution with a brute force approach, consider how the naive method would operate. A brute force approach might involve repeatedly scanning the array to find and remove the smallest and largest 5% of elements. This would require multiple passes over the array, leading to a time complexity of O(n squared). The space complexity would remain O(n), since a trimmed copy of the array would still be required. In contrast, our optimized solution leverages sorting, reducing the time complexity to O(n*log n, while maintaining O(n) space complexity. By slicing the sorted array, we avoid unnecessary repeated traversals, making the solution significantly more efficient. Importantly, whether we analyze the best, average, or worst cases, the time complexity remains O(n*log n, as sorting always dominates regardless of the input distribution. In summary, this solution achieves a time complexity of O(n*log n and a space complexity of O(n). These results make it highly efficient, especially for large arrays, as it minimizes redundant operations by leveraging the efficiency of sorting and slicing. Compared to a brute force approach, this optimized method demonstrates clear advantages in both time and space efficiency, making it a robust choice for solving this problem. When solving this problem, there are a few common mistakes to watch out for. First, forgetting to sort the array before removing the smallest and largest 5% of elements is a frequent error. Since the problem depends on identifying these extremes, sorting is essential to ensure the correct elements are removed. The second mistake is off-by-one errors when calculating the number of elements to trim. For example, when multiplying the array length by 0.05, rounding issues or incorrect integer division might lead to trimming the wrong number of elements. To fix this, use functions like math.floor or int to handle rounding correctly. Finally, not accounting for edge cases, such as small arrays, can cause issues. If the array has fewer than 20 elements, trimming 5% could remove all or most of the array. Always check the problem constraints and validate the input size, though LeetCode typically handles this in its test cases. Another common mistake is miscalculating the mean after trimming the array. Once you remove the outliers, it's crucial to use the updated array length in the mean formula. Forgetting this step will lead to incorrect results. Additionally, for large arrays, inefficiency in your solution can become a problem. While sorting is necessary, performing extra operations like repeatedly creating subarrays can significantly increase time and space complexity. To optimize, minimize redundant steps and use techniques like slicing effectively to trim and process the array in place whenever possible. In interviews, focus on key strategies to tackle this type of problem efficiently. Sorting is often the backbone of such problems, as it simplifies finding and removing the smallest and largest elements. Once trimmed, calculating the mean is straightforward and can be done in linear time, but be mindful of avoiding extra overhead. It's also important to discuss edge cases, such as handling arrays with duplicate values or very small sizes, to show thoroughness in your approach. Additionally, be prepared to explain the time complexity of your solution. Sorting dominates at O(n)log n, which is optimal for this problem, but you should be able to justify why this is the best approach given the constraints. There are also alternative approaches to consider, each with its own trade-offs. The default sorting-based approach involves sorting the array, trimming outliers, and calculating the mean. While simple and intuitive, it comes with an O(n)log n complexity due to sorting. A heap-based approach, on the other hand, uses min heaps and max heaps to extract the smallest and largest k elements directly. This method can save time by avoiding a full sort, but it's more memory-intensive and has a complexity of O(n)log k. Finally, for specific scenarios like large datasets with limited value ranges, a bucket-based approach may work. This method uses bucket sorting to identify and remove outliers quickly, making it faster in certain cases, though it is less versatile for general inputs. Each method has its strengths, so choose based on the problem requirements and constraints. Great job! To summarize, We tackled LeetCode problem number 1619 by leveraging sorting to calculate the trimmed mean efficiently. We also discussed the importance of this technique for handling outliers. Thank you for watching. Don't forget to like, subscribe, and stay tuned for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!